Um, it's a great pleasure to welcome Abram Detofsky. Abram has a BS in microelectronics from RIT and an MS in electrical and computer engineering from the University of Arizona. Over 20 years ago, he started at Intel working on the design validation for the Pentium 4. Then he moved to test pathfinding, where he drove module test method and software along with prototyping for Intel's first internally designed manufacturing test system for high volume manufacturing. And then after working on pathfinding and development, he now leads the test architecture definition team for Intel's future chiplet-based products. He is also the chair of the IEEE Electronic Packaging Society Test Technology Committee. That's a lot of acronyms there, and is on the advisory board for MEPTEC. So with that, we welcome Abram. And please ask your questions as he goes, and I will ask them at appropriate times.
Absolutely. Thanks, Ira. So yeah, I'd like to present, in this presentation over the next 20, 30 minutes. I'd like to give everyone a feel for some of the work that we've been doing as a group, right? This is really a team effort in our IEEE, Electronic Packaging Society Test Committee. And you'll see a lot of the co-authors here in this title slide. So this is definitely a group effort. And really something that's near and dear to my heart, which is how do we test as an industry, as a corporation, as a company, as a community of partners, chiplets, and how do these effectively work in a overall product kind of moving forward, and how does test and testability fit into that overall picture? And what we're finding is, and what we found, over a year ago when we started this effort, that there is a lot of scattered work that's going on right now across the industry, and there wasn't really a whole lot of focus in kind of bringing this together and really giving guidance to an integrator like Intel, like Amkor, that's trying to create a real product that's sellable to the outside market, using chiplets, using tiles, your favorite word for the term. So this effort kicked off basically a year ago as part of our IEEE effort. And the fruition of this came about at the end of last year in December, where we released the first version of this guide, this practitioner's guide, this useful guide, I think, for anyone that's really trying to make a product in this area moving forward. So that's kind of where this kind of intro to that effort is about. So let's take us through it. All right, so the agenda, we'll look at the rise of chiplets. Why has it been such a challenge in more recent years? And it's going to be more of a challenge kind of moving forward. Why is that? And we'll go over some of the testability gaps. What are the specific problems from a chiplet perspective, from a tile perspective moving forward? Where do we see, or have we seen some of the things where the standards have fallen down at the moment? So then we'll go over what is the purpose of our BKM. Is this a standard? Is this a document? How should we use this long term? And what's inside it. So I'd like to kind of give at least a peek inside. I'm not going to be able to go through all of the content, certainly. All of this content is available for free for anyone to download on the web. So there'll be links in this presentation for people to go off and get your copy. But I'll give you a flavor for what's inside for some of the great work that's going on at the moment, or that we've included. We'll pull out some key findings again, not all the key findings, but some of the key, the summary key findings that we've come away with that we thought would be useful to convey to this forum moving forward. And then there'll be a summary and call to action at the very end. All right, so the meteoric rise of chiplets. I think for a lot of folks on the bridge here and, in the future, I think it's probably of little surprise that the industry adoption of chiplets has really accelerated, really a lot faster than really anyone has anticipated, in the past, either based on some of the road mapping that's been done or otherwise. The attach rate to disaggregated type products that are based on chiplets has accelerated, and it's highlighting a great many critical testability gaps, because it's outstepped or outpaced the rate of standardization that has gone on, and kind of agreement that has gone on between companies long term. We'll get into that in a second here. So before we go into some of the nuts and bolts, I think it's useful to kind of settle on kind of a definition of what a chiplet is ultimately. I think there's lots of definitions out there. I've personally gone to Wikipedia for my version of that definition. I think this is a useful one. Kind of highlighted some of the key elements here. A chiplet is a tiny IC. People could argue, okay, what does tiny mean? Is it a certain square millimeter area, transistor count, et cetera? But I think a more useful constraint is, it's a well-defined subset of functionality. It's a self-contained, well-bounded sandbox, if you will, of functionality. And number two, it's designed to combine this sandbox of functionality with other chiplets, with other sandboxes, with also similarly defined, well-defined boundary conditions. And these sandboxes can be, brought together in a mix and match Lego-like assembly. So if we think about chiplets and heterogeneous integration from that perspective, you could have tiny chiplets, you could have medium-sized chiplets, you could have, full reticle-sized chiplets, and they would follow this definition as long as they have well-defined interfaces and are designed to be used with other chiplets or other ICs. So that's the definition that I really have. And as we see in the industry today in terms of technology that's implementing these, we see solutions that are based on silicon-based kind of solutions, interposers, whether they're full interposer, kind of full reticle tiles, or whether they're tiny little EMIB type things from Intel or otherwise, or they're organic based substrates, which are more generic and lesser expensive from die to die. So there's a plethora of different technologies that can implement various levels of chiplet design solutions, which target different markets, different cost targets ultimately. Okay. All right. So this, as I mentioned or alluded to a little bit earlier, has highlighted a number of different significant testability problems from an integrator perspective. So suppose you're an integrator like Amcor or any sort of a solution provider that's trying to use multiple chiplets, which may come from, your own design house and or other design houses or even fab processes across the industry. Assume that there's this marketplace that's out there as an example. Bringing these disparate pieces together is a particular challenge. And we've put together as kind of part of this BKM, kind of a diagram kind of showing a generic assembly. We have a package, we have an interposer or bridge. We have one or more die that could be stacked vertically in 3D or 2.5D kind of assemblies. But kind of marching around the document or marching around the diagram, maybe counterclockwise a little bit. There's right now quite a bit of missing multi-physics co-design modeling tools that can bring together not only the modeling for an individual chiplet, but how do you now model and simulate power? How do you model and simulate self-heating events? Not only in mission mode, but also in test modes, which tend to be quite a bit higher power for various reasons. In this full chip assembly, it becomes incredibly complicated when you have different chiplets under different load conditions, under running different executing different content to understand how a neighboring chiplet will affect an adjacent one, kind of long term, both vertically and horizontally. So having some way to kind of pull all of this together and share information across the industry is a big challenge. We're missing also interoperability. So we have a number of standards that are supported or that are supportable out there. We have AIB, we have a bunch of wires, OpenHBA, Ultralink, HBM, MDIO, UCIe, the new kid on the block from Intel. So lots of standards, but if you look almost universally in most of these, if not all of these standards, there is a desert of information in terms of testability and testability definition that we'll get into here in a second. It becomes a big problem when you have one die trying to talk to another die or trying to verify an interface from one die to another die. Let's say one die implements, a BIST engine using PRBS9, and another die, the adjacent die, implements PRBS 13 or 31. They're obviously not going to be able to talk to each other and margin each other, since the data streams would be different from a generator and checker point of view. So unless you can agree on a minimum viable DFT, design for test feature set, you're not going to be testable, and you won't have a product at the end of the day that you can actually sell to a customer. And most designers don't, or well, historically haven't appreciated that. I think some are coming around to that fact moving forward. Disag is also significantly driving up the cost of die and package test. As I think in one of the next presentations from Samir today, we'll kind of talk about this economics and how this is becoming a huge problem for the integrator long term. We're missing trusted, shared, encrypted, multi-party test content and data. Being able to share data between a fab house and an assembly house is actually critical in this area for debug, for customer returns, for guaranteeing quality, to guarantee reliability long term. Without this information pipeline, which, to be honest, most suppliers are very reluctant to share, you're not going to have a product at the end of the day. So this becomes a huge, huge problem, with these lack of standards today. So to have encrypted, anonymized, and shareable data. From a design perspective, there's missing EDA tools, flows, methods for these various interfaces right now. So, it's great to have a specification, but unless you have the full chain of tools that can be brought to bear for both, design, for DFT, for pattern generation, content execution, and, access, you don't have a product. And that standard will not be adopted internally, or not adopted very widely, without a lot of human glue and a lot of, very specific glue that's created. And just from a comprehensive debug and method strategy for fail modes, understanding the fail mode models as well, just being able to detect, if there's a failure between die 1 and die 2, who's at fault? How can we determine which side, which link? Is it the transmit side? Is it the receive side? Is it the interconnect side? Or sometimes multiple elements that are broken. So what is the strategy around that? And that requires an agreement between die 1 and die 2 manufacturers and designers to put the same features in place to allow that visibility to be surfaced at the end of the day. So a number of problems. This is not an exhaustive list. There are more that I'm sure that people can probably spout as well that are not in this list, but these are some of the bigger ones that kind of surface from the analysis that we did last year. All right, so like I kind of rattled off a little bit earlier, there are a number of standards out there. The great thing about standards, as someone once said, is there are so many to choose from. So kind of tongue in cheek, but there's the advanced interface bus, 1.0, 2.0, the bunch of wires, the effort from ODSA that's open sourced, the new kid on the block, like I mentioned, the Universal Chiplet Interconnect Express (UCIe). There's of course the JEDEC HBM for the memory stacks that many of the advanced products use today, as well as HBM2, the successor to it. Lots of standards, but really a lot of these, if not most of these, fall really far short in really defining what it is we need to do, and standardize from a manufacturing test point of view and a manufacturing debug point of view. And without that, you don't have a product at the end of the day. You cannot sell something. So what we've tried to do, and I think this is probably the first in the industry to try this at the moment and publish this, is we put together a testability best known methods BKM. And really, this is a freely downloadable. You can download it today, right now, as you listen to this. The link is here, and you can go directly to the download document or to go to our EPS test website, which has the document prominently displayed on the front page with a download link. But basically, what this tries to do, think of this document as a compass. This is a best known techniques that anyone, whether you're a designer, whether you're a product engineer, whether you're an architect, an EDA supplier, you can come to this document and kind of figure out your way in this complex heterogeneous world that we're in right now. It ties together, doesn't try to replicate specifications that are out there, but it tries to point you towards them as appropriate and fits things together into a overall narrative that is relatively cohesive, I would say, that can point you in a successful direction. So you can actually basically take these pointers and techniques and kind of internal, best known methods that are kind of built in to improve your success as an integrator, as an EDA supplier, to kind of achieve what are ultimately what we need to do is create this sellable products at the end of the day. So it's built with. Go ahead. Mm-hmm.
So maybe here's a good place to ask you: how does a BKM differ from a standard, and should this be a standard?
Yeah, no, it's a good question. We've kind of tossed this around if this is a standard or not, and we've kept this intentionally as a BKM for now. And really, this is a add-on adjunct supplement to the existing standards that are out there. So our hope is that the standards, as they mature or continue to mature, we're not trying to replace the standards that are out there, but as they continue to mature, that they will start to pull in elements as appropriate from the BKM into future versions of the standard, so that they now then will comprehend some of these requirements that are not, these suggestions, these ideas that we're putting into the BKM, and ultimately, ideally, the BKM wouldn't be needed anymore, because the standards would then fully encompass everything that's needed fully within the standard. But the BKM itself is not intended to be a standard that overrides or overrides or replaces an existing standard that's out there. So that's not that intent. So it's a helper document to go along with an existing standard that may be deficient in some way today.
Got it. So in an ideal world, each of the standards would have a testability section, or
yes.
address all.
That would address all the concerns, all of the concerns with minimal viable kind of feature sets and every different. Yeah, exactly. Yeah, but we're not there yet. So that's where the BKM comes in, to try to shore up this really gaping hole right now from a testability perspective. Okay. So the other point I want to bring up as well is that this document complements the Heterogeneous Integrated Roadmap, which the IEEE EPS also owns. So this is a long-term kind of 5-year vision, ultimately. So our BKM is today. It's not trying to address, what's happening 5 years from now, 10 years from now. It's really, okay, what are the best known methods of right now? So from that perspective, we think this nicely complements the current HIR roadmap that's currently being published on a yearly basis. And the intent is for this BKM to be revised in concert with the HIR on an annual basis. So every January, February, there'll be at least another version of this coming out So this will be up-revved with new information as we see fit based on the authorship. So again, this is authored, ratified, IEEE EPS. Go get it. Here's the link. Easy to kind of jot down by hand. The document itself, maybe not so easy to jot down, but it will be in the published materials. All right, so what's inside the BKM? So we have a number of authors that we've had on the front page as an example that authored different subsections within this. It's about 76 pages, so it's fairly lengthy. Our chapters within the document are designed to be read out of order. So you can kind of pick this up, scan down the table of contents, and jump to whatever section that kind of tickles your fancy for the most part. So the themes and sections, that we have right now, this is not going to be an exhaustive, detailed list of everything that's built into it, but in terms of major sections, at least. We're going to go over the ecosystem and test economics, and I want to also point to Samir. He'll be presenting later in this workshop, actually today. So hang on for lots of great detail in this area and really understanding how we as an industry need to kind of design our products and what some of the call to actions that are needed in this space to make these successful economically as a viable product. We'll look at where we have die probe strategies and best practices. So Will Thompson authored this section. He'll also be presenting later in this workshop tomorrow. So stay tuned for that. We have an interconnect best practices, redundancy, repair, and rework. So Srijit presented a subset of the content actually in last year's Chiplets workshop. So here's the link to his YouTube video if folks are interested as well. So debug, fault isolation, best practices. So this was a section that Terrence Tan presented last year as well in the Road to Chiplets workshop. And again, here's the YouTube link to that. The changing nature of AT and test cont delivery best practices. So, how is functional tests, how is structural test evolving over time? How does the AT community need to adjust to what we're seeing in this space? We have a section on database and data sharing best practices. Some good consolidated work here, as well as pointing back into the HIR that we have as well. HIR product deployment checklist. So one of the things that we felt was needed and strongly needed by the deployable community is, we're missing a checklist. It's nice for designers or for integrators to kind of run down, okay, am I missing something, something big? And sometimes it's not always obvious if you're, creating this a chiplet-based design for the first time. So having, things like, am I covered from a legal perspective, as an example that people may not think about initially, where it actually becomes potentially pretty important, especially for things like customer returns, making sure you're thinking through that process. Having a checklist in place before you kind of pull the go gun or the trigger is actually kind of useful. So what we're trying to do here is kind of create a first stab at, okay, what does a checklist look like if you're deploying something as an integrated product? One of the things that we want to watch out for. And lastly, which, there's been a lot of resonance for within the forum as well as outside the company or outside the forum from IEEE, is a number of case studies. We've pulled together a number of case studies from across the industry. What's worked in a heterogeneous kind of world, type product deployment, and maybe more importantly, what hasn't worked in the past, and some of the key learnings and learnings from kind of each of these. So definitely invite folks on the bridge here to download and peruse. And give feedback as well. What's working, what doesn't, what are some missing sections that would be really useful in the future that we can entertain putting in the next version of the document as well. So we want this to be useful to the community at the end of the day and regularly updated because the technology is evolving so quickly long term. All right. So I think from a key learning perspective, there's a fundamental need for multi-supplier chiplet test interoperability. I think the key word here is interoperability. If people take nothing else away from it, it's a long, sometimes hard to pronounce word, but interoperability is the name of the game here. We need harmonization, to allow us to, cooperate to a degree that will allow us to later on compete appropriately in the marketplace. So we need harmonized EDA tools, methods, and flows. That's core to all of this in terms of adoption of an interface specification or otherwise. We need a harmonized set of minimum viable DFT. We don't have to specify every single DFT on an interface, but we have to agree on a minimum viable one that will allow us to debug, that will allow us to manufacture, that will allow us to process customer returns effectively. All of that needs to be defined for test, for full debug assembly, for partial assemblies as well. Think stack-based testing as an example. We need advanced probe technologies and really coming together on what those KGD testing strategies for both die level, stack level, partial assembly, full assembly at the end of the day. And we need portable test content and a secure supply chain that we can use for data sharing, package assembly analytics long term. So there's a huge opportunity here, I think, as an industry to use different key cache phrases, AI and other things and data feed forward to really make a smarter and more nimble supply chain and data analytics ecosystem within and between companies that need to share information. But I think that's absolutely key and something that's really in the early infancy at this point. So I guess from a summary and call to action, the key point here is our BKM is really a tool. It's not something to replace anything. It's something to supplement. Our chiplet ecosystem. It's really trying to help people, help companies, help suppliers, partners navigate what it is today a really fragmented design and integration space, and kind of consolidate some of these best methods, known methods today, which will obviously change in the future over time, that we want to keep updated and keep pace with, but really trying to make sure that people are successful because no one company, no one partner can own all of this, the vertical, long term. If we want to build out a successful marketplace, chiplet type of marketplace, we have to build in the assumption that we're only successful as integrators, as chiplet suppliers, as EDA suppliers, if everyone is successful in this business. If we don't, we are selling ourselves. It's going to fall flat, effectively. So, to do things at scale, we need to come together to a certain degree to allow us to compete, I think, is the key. So, but our testability document itself is not sufficient. So, from a call to action, what I want to say is, as an industry, we really have to decide now, where and how we need to cooperate. Sometimes it feels a little bit strange for some companies to do this, but I think if we're talking about a marketplace which is open and that's vibrant, that's interoperable, we have to agree on certain standards, certain minimum viable standards for that marketplace to really take off and successfully, to allow us to successfully compete. So, I think my call to action is really we have to come together now and work through the various forums, the various standards to improve them, to work such that they basically enable this marketplace that we're all trying to kind of move towards and enable. So we have a really great workshop panel tomorrow that Zoe Conroy will be leading us through in MEPTech. So please stay tuned for that and sign into that. But I think we've got some really exciting panelists. And the topic is this coopetition concept that I'm kind of bringing forward here. How do we standardize? How do we cooperate? What are the things we need to do together to enable this marketplace such that we can compete effectively moving forward? So please stay tuned for that. All right, and the legal notices at the end. So yeah, that's about it. Any feedback or questions?
So, Abram, why don't you flash the legal notices up, and then we'll go back to the questions, and then okay, done. Check the box. Okay,
Yes.
so let's go back. So how should an engineer really use the BKM document? You talked about it's designed to be read out of order. You talked about, picking what you want, but how do you see the typical engineer, the test engineer, or the designer using?
Yeah, the BKM document is designed, like you mentioned, to be read out of order, but it's really it's a great intro, I would say. At a minimum, if someone's not familiar with this space intimately, using this document, reading, at least initially this document, this is a great compass. This will point you in the direction of all the relevant standards that are out there. This will point you to the HIR relevant sections for test and testability. This will highlight all of the really big rock problems that we have today and some of the ways that we're looking at and solving that today through various partnerships that we have throughout throughout the industry at the moment. But really, this is, I think, for the first time we're kind of using this, or we have available now a compass that we can use, that EDA suppliers can use to really fill in some of the gaps that we have today in the current standards that are out there. So it's a great starting point for folks to go to say, okay, what's the state of the art today? Where are the problems of today? And how, as an integrator, as an EDA supplier, how can I be successful moving forward? So think of it like a compass.
Okay. And help point the path. So let's see if there's some questions from the audience. Please put your questions in the Q&A tool on why people are doing that. You've obviously, in your work, worked with a number of the standards so far. I like to pick on the old RS-232 as the most non-standard standard in existence, in that there is so much flexibility in the definition that you couldn't just plug two cables together and expect them to ever work. So yes. Are the current chiplet standards, interface standards, sort of that way with a lot of flexibility, or are they well enough defined that if two devices have, quote, that standard, they will mostly play together? Like let's say USB, for example, at the other extreme.
Yeah, I think most of the standards from if you kind of dive into them, they define fairly well the electrical interfaces to make sure that they play well together, assuming that they're both following the same standard. From a mission mode perspective, right? Okay, you can move bits from point A to point B effectively at a given data rate with a given error loss. But where they kind of fall short and fall apart is, okay, now how do we validate that interface from a testability perspective? How do we handle redundancy? How do we handle who's at fault when there is a problem, kind of thing? Those aspects are typically missing from a standard. So yes, they'll play well together, typically, if they're following a common standard, but they're not manufacturable, or not necessarily manufacturable without a lot of secret sauce behind the scenes, which is fine if you own both sides of the link. If you're a design company or a more vertically oriented company that owns the design on chiplet 1 and chiplet 2 for a given standard, you can put all that stuff in place without telling anyone effectively. You can still get it wrong, obviously, and we've seen lots of instances for that. But if you're now running across different suppliers, which historically haven't shared that level of information because they never had to, from chiplet 1 to chiplet 2, which may be on different processes and different suppliers, different design companies, that's where things will fall apart, almost guaranteed, unless we very intentionally define this minimum viable feature set, DFT feature set. Just letting it happen or assuming that it will happen on its own is a recipe for failure in this business, unless we have to put a lot of intention around this, these missing pieces, which are not today in normal specifications.
Understood. I got a good idea of the picture. Let's see, one comment, and just a reminder to everybody, please use the Q&A tool, not the chat. Here's a question. Would you consider including examples in the BKM of corporate collaboration models that negotiate the design IP issues for developing acceptable test methodologies? So you want to comment on that?
So the idea or the thinking is success stories in how multiple companies have come together to initiate a successful product in this case. Now that's a great example or a great idea to put into kind of the next rev. I don't think we have an example per se in the case studies for that. But I think that is an excellent example. So I've taken a note here.
Okay, good. And then there was a question about challenges in microbump probing, but I believe Will is going to address that tomorrow. So
yeah, we'll pull that in. So yeah, stay tuned for that. Will has an exciting presentation all lined up for that right now.
Yeah. Okay. Are there any other questions from the audience? And if you haven't taken a moment to give Abram some feedback, there is a poll that should have popped up on your screen. So please take a moment to just give him some feedback on his presentation. And with that, I think we will move on to the next presenter. Thank you, Abram.
Great, thank you.
And once again, I'd like to thank the sponsors, our diamond sponsor, Amcor, with differentiators in technology, quality, and service. And our emerald sponsor, Advantest, receiving the highest ratings for customer satisfaction from the VLSI survey for 2 consecutive years. I would like to thank both of them for sponsoring today's event and tomorrow's event and sponsoring the Road Chiplet series. And with that, I will wish everybody a good day and look forward to having you join us again tomorrow. Thank you.